Okay, so thank you for the opportunity to talk here, and it's very nice to visit here again. So that's the title. The title is something like conditions. For small modular well, it doesn't assume it will be more clear from the top. And this is joint work with block.
Cześć.
Znaczy się bez sensu zupełnie, nic nie widać.
Nie, no co ty, teraz lepiej. Poprzednio nic nie było widać, a teraz to w porównaniu...
Obraz się stabilizuje po chwili.
Overstiegen, Bloch.
Ale to jakiś totalny bezsens. Chyba trzeba zacząć chodzić.
No ja przepraszam, ale jestem po prostu tak zawalany robotą. Mam w czwartek Radę Instytutu, robię sprawozdanie.
Krzysztofie?
No nie mogę. A, przepraszam bardzo, już się wyłączam.
No one.
Okay. Go on.
So this is the team which I suddenly joined, and it was at the beginning of this year when I came across a preprint written by this team about upper bounds for model of renormalization. And I immediately tried to apply the result to, say, infinitely renormalizable quadratic polynomials bound moduli from above. And first I thought that it gave some interesting result, but eventually I understood that the statement did not give any non-trivial result, just some bound from above. And then I contacted Bloch, and it turned out that also the method of this paper also didn't give non-trivial result. And then we started to discuss, and then I think we got some interesting and in a sense maybe some surprising perhaps results. So that's what I'm going to report. And this is in fact still work in progress, some progress. Okay, so the plan of my talk. So first some few definitions that I reuse. Then two well main results. So bounds for moduli, and then I hope there will be some introduction, but infinitely reliable. Okay, so infinitely renormalizable maps, and here definitions and introduction. Introduction going to be and then some corollaries from this to this, to infinitely renormalizable. And maybe maybe if I will have energy and time, I will talk about there is theorem here with some conditions, and all conditions are necessary. You cannot drop conditions, and one condition is especially interesting, and there is an example which shows that also this condition also necessary, and it uses Lavar's map. Okay, so this is the plan. I will be talking about polynomials, but all the results are okay for rational functions. We don't use polynomial technique like external rays or something like this, so just don't care about this. So that's why it's okay for rational functions. Well, one should use a different metric, but otherwise. But anyway, in my talk, F, I think, will be always a monic center polynomial, some degree. So monic means okay, this is one thing. So that's always polynomial dynamics. Now let me recall what the polynomial-like map is. This is this triple, so two topological disks on the plane. U compactly contained in another topological disk V, and a proper holomorphic map P. Of some degree, at least this type. Okay. This is what is called a polynomial-like map, and there is associated field in Julia set. This is just the set of non-escaping points. And I always assume that this field in Julia set, this is field just without in field Julia set. I always assume it is connected, which is equivalent that all critical points. So this map, this function has d star minus 1 critical points, counts and multiplicities. And connected, it is equivalent to say that all of them are non-escaping. So it means that U minus this set contains no critical points of P. Okay. And a few more notations. Okay, let me put us here. usually this n, so the picture looks like this. Okay, and this is this star covering holomorphic map. And this annulus V minus closure of U is called usually fundamental annulus. And we call, and here is the field in Julius, which is okay, and that U minus K, the field in Julius set, we call it root annulus. And we are caring about estimate, upper estimate for the modulus of the root annulus. Modulus, so of topological annulus on the plane, you can define it, you map it by a Riemann map, conformal isomorphism onto standard round annulus with this radius, and modulus of this is by definition modulus of this, which is this. So this is really conformal environment. Okay. So this is definitions, and of course there is a straightening theorem by Douady and Hubbard. Which says that there is, in this case, because I assume this field Julius set is connected, there is a unique monic central polynomial G, okay, of the same degree, at this star, which is the breed equivalent to P, which means that there exists a quasi-conformal homeomorphism H, which is conformal on the field in Julius set, almost everywhere. Exists by derivative 0. Which conjugates, so say C, then should be diagram should be committed. So H G H on U, something like this. Okay. Maybe there are relations between moduli of different, so modulus of v minus is equal to so knowing the modulus of the root annulus, then you know modulus of this annulus, and also an estimate for the modulus of fundamental annulus, of course, because by the Dutch inequality, modulus of fundamental annulus, the star to the power n, and okay. So but not vice versa, I guess. So we estimate modulus of root annulus. Okay. Okay, so maybe another definition, or maybe more definitions, I will state some results. Okay, so what we mean by renormalization? Renormalization F is renormalizable anyway. The polynomial-like renormalization of F is a polynomial-like map in this form. So this is polynomial-like map of some degree, the star. And we always assume that field in Julia set is connected. Okay, so this is T. Well, and different, so proper subset of field in Julia set of F. Okay. Now, there is a polynomial-like cycle.
And do you assume that degree is the same as?
It could be the same. It could be the same degree.
Now I just wanted to say that we go along, we don't capture again the same critical point.
Yes, yes. Critical point cannot belong to two sets of the orbit of this. Yes.
So it's the same degree as the.
Yes. Same degree. So let's consider polynomial-like cycle associated with this. This is just the orbit of this. And then each of this set is also a polynomial-like map. Also filled in Julia set of some polynomial-like map of the same degree. Okay. But we assume more. We assume that a renormalization, always assume that a renormalization is simple. Which means this. All the sets are pairwise disjoint. Okay. All elements of this cycle are pairwise disjoint. And in this case, the renormalization is called primitive. Or this orbit is split into, say, R groups of each of them in each group are S elements. Okay, so it means that Q is equal to R by S. Let me continue here. Such that all sets in each group have a unique common point which does not separate each of these sets. Well, I mean, that's should be clear. Okay, so and in fact, this point is the point. All these points form a cycle of period R. For example, RS2 is 3, so the cycle of period six, and FR interchanges, permutes sets in each group. Okay. Okay, and this is the cycle of period 2 for F. Okay, so it's clear.
Here you have 4 sticking out instead of the left hand. So
Yeah, it's too much.
there should be 3 in both.
There should be 3. No, it's too enthusiastic. Okay. Now it's okay. So maybe this is the last, another definition, last one. So we call element of this cycle element, of course, element, that's small Julius. An element of this cycle of the form f of k, where k contains a critical point of f, not f q iterate of f, but f. We call it critical value. It's critical value.
You have only one question.
No restrictions.
It's not z to the power of b plus c more than
No, it's central general, yes. But there is restriction for the degree of this polynomial-like map. I think the degree is bounded to the power d minus 1 always. Because in the worst situation, you can have d minus 1 simple critical points, say on different elements, and each time degree is multiplied by 2. So this is bound. So knowing d, you know the bound for degree of all such maps. But otherwise, no restrictions also. Maybe okay, so it is not equivalent saying that this contains some critical value of f, because in principle critical value of f can come from a critical point which is not in this cycle.
But along the cycle, you need only once a critical point?
No,
Several.
several.
So this was my original question, whether
No, but there is no critical point in intersections of two sets of the orbit. This is the restriction.
so
But
again,
otherwise there would be
So
some.
along the cycle, can you meet several times the same critical point?
No,
The same is on the one.
only once, but different.
But different, you can meet different.
Yes. Okay, and now I am ready, I think, to state theorem. So of course, this situation is called sample length of base period R, period of this cycle, and relative period S. Relative.
Am I right that it decomposes into two renormalizations? One is satellite, another is relative. You have a renormalization for a long cycle, but only even in your picture, you have in fact a renormalization with period 2 and then.
Yes, of course, yes.
Decomposes.
I'm not sure about 2, but
primitive and satellite.
But period.
That's on your picture. Primitive and satellite.
No, it's not. It's not clear. Of course. Okay. So of course, No, I don't think so.
First, you renormalize with a period 2.
You mean there is a kind of some field Julia set
Yes,
that contains
here and here.
all this of F2?
2, yes.
No, I'm not sure.
That is, and then.
No. The union of this small Julia sets is not a field Julia set of some other. It is not.
Okay.
No, it is not. For example, for quadratic.
To what I'm saying.
For example, for quadratic polynomial.
No, I understand. You remove first after the first primitive. You remove part of Julia set, and then you
Yes.
apply satellite, and you remove again some part of Julia set.
Yes.
You obtain.
Yes, but even there are several
By
renormalizations.
definition, that is decomposes.
No,
Okay. go
I
on.
don't see.
Yeah.
There will be.
It's not a fundamental.
No, that's there will be many times renormalizable, but then. Okay, so theorem A. So assume that F is renormalizable. Satellite renormalizable. Of a relative period S. And I don't care about base period. There is some base period, it could be 1, could be bigger than 1. I don't care. Now, what I do care is about, let's denote by D, the minimal diameter of critical value elements of this correspondence cycle. The correspondence cycle. Okay. Then for any root annulus, it means just you take, as I said, each such set is a filled-in Julia set of some renormalization set. You can take any representation of this as a polynomial-like map and take root annulus of this. Okay. There is this bound modulus root. And this is the degree, the star. And here 1 s d square. I mean, maybe you should divide it by 60. But this is about. So what is interesting here? It is independent on the way on the period of base side. And this is bounded by 2 to the power d minus 1. But of course, there is this. What is S? S is a relative period. So the number of elements Fr. There is some rotation number associated to this point, okay? And S is the denominator of this relation.
So can the denominator be negative?
No, it's always positive. No.
It's
Okay.
a non-trivial thing.
Even if it's I hope well, there is no any denominator. S is just the number of elements. Okay, so this is one theorem. For example, let us state it for quadratic polynomial, and for base period 1 and then relative period is just the period in the base period. So here is a picture. So F is a quadratic. Now, and then which is a primitive satellite renormalizable of base period 1. It means that alpha fixed point is the common point for all small Julia sets. So it looks like this. So S here is for mathematical whole. But all this is inside of big Julia set of quadratic polynomials. So okay. So this is symmetric, but as there are some. Okay, so everything is inside of this. Then this D, so the critical point element this distance is just modulus alpha, but the multiplier is at least 1. So this distance is at least half. Okay. And then this the critical value element is at least square of this. Okay. And then you write down bound for modulus. And the star is the plus 2. This is 4 pi over 1 S over 4. Okay. For example. No. You are right about 0. Yes. Because I didn't, because I cheated here. For each S, at least L over D square for some absolute constant A. Something like, I don't know, maybe 16 square. So
Non-negative denominator.
And by satellite, you mean that R is 1 in this theorem. When you say F is satellite.
no. If any base period. No, base period can be the same in this theorem. This is the point. Sorry. over n, where your question is very encouraging. Because I recalled something more and more. So n is the number of critical points of f in the whole orbit. Okay, number of critical points.
With multiplicity.
No. In this PL cycle. But anyway, n is bounded by d minus 1, so that's it. So you can write it down 2 pi 2 to the power d minus 1 over 1 s d squared over d minus 1. And this is for all s, when this is just bigger than some absolute constant.
But then I'm still a bit worried about the absence of R in this estimate.
Don't worry.
So R can be added.
Yes, that's the point. In first variant of the series, R was 1. This is the second variant.
Because naively, it seems that when R becomes very big, then D will be as small as you wish.
Yes, you are right. In general, of course, D is a parameter here. So I don't claim that D is big. Of course, D should depend on R.
Yeah.
But when there is some general bound of D from below, which depends on R. I can even write down this bound. But
that means that sometimes this thing you have under the logarithm is less than 1. So
Yes,
then
but-
no,
what is the-
because of that condition.
Whatever else, not
Because of your another question.
And that's regardless of R, even when R is very big.
No, there is no R here. So there is D as a parameter, no R, just D.
I see.
If you want to apply it and don't know D, but you can write down a bound.
So then maybe I misunderstood. What is D? Could you define what D is? It's minimal from what set?
You consider the polynomial-like cycle,
Okay.
this cycle, and mark elements here, small Julia sets, which contain critical points of. Then images of these elements are critical value elements.
Yes.
So it must D minus 2 of them.
Yes.
It is independent on the degree of on the number of elements. I mean, bound elements.
Right. So it's the minimal diameter among what components?
Critical value elements.
Critical value elements.
There were
One among critical value elements. Okay. I see.
Okay. So in particular, if there is a sequence of quadratic maps which are like this, satellite renormalizable, immediate satellite renormalizable with periods tending to infinity, then post moduli of all possible root annuli tend to 0 uniformly. But this is about satellite renormalization. We have something about not necessarily satellite, in general case, but without bound explicit. Okay. So this is another statement I want to write down now, and then comment on this. So theorem E assume that there is a sequence of sequence of monic center polynomials of say the same degree, which it doesn't matter whether mathematical center but they converge to a polynomial of the same degree. Okay. Now, they assume that that each Fn is renormalized. So there is some renormal-like map for each Fn sitting inside. Okay. A sequence of polynomials, sequence of polynomial-like maps. Now assume also the following three conditions. And I denote by K star n the field Julius. This polynomial-like map. Okay, so I assume that Qn tend to infinity. First. Second, the sequence of continua converges, well, you can always take subsequence in to some continuum, K star in the Hausdorff method. Such that this is non-degenerate. Diameter of the limit is positive, so it is not important. And the last condition is that this continuum K star is not in a basin of attraction of a parabolic cycle of F. Okay. And then the conclusion is that the moduli of this core annuli of VM this is and I claim that you cannot drop no one of this condition. No one of this condition.
Parabolic also you cannot.
Yes, that's the example is about. Example of when the all holds and this is away from zero, but it isn't parabolic. And this is a non-trivial example. Maybe it was known, I don't know, but I asked one string, he didn't answer. Because my our example is goes like this. So we know universal complex bounds for renormalizations of real unimodal maps. Okay, it means that in fact an example can be constructed only on the real line with periodic intervals. Okay, but this is not real. This you use Larsen map. I hope I will draw some pictures. Okay. Okay, so this is. Okay, now let's talk about applications to infinitely renormalizable. Another definition. So f is now just one f, and assume that there is a sequence of polynomial-like cycles. Such that no, there is well, it's what doesn't work. I mean, if I mean by this that each element of this is proper contained in some element of this.
Factors for renormalizations.
Yes, that's very defined. Either primitive or satellite. And then there is this intersection.
They contain critical points.
They contain
Which elements of the these are the whole cycles?
whole cycle.
So union of these
Yes,
small things.
Not you, yes. It's not
Here in the section, yes, but here the union in the cycle. Okay.
the cycle.
So cycle is the family and the orbit. Cycle.
The orbit. So we call it the infinitely renormalizable set. In this paper.
J infinite.
J. All names in the paper are due to such a block. That for me doesn't matter. Okay. Okay, so if Pn is a period, the number of elements just in Pn, or period of each element there, then the ratio is some integer. Number of elements of Kn plus 1 in each element of K. This is the general. Then let's call it infinitely renormalizable. And well, usually if this sequence is bounded, then then the renormalization is called bounded quadratic. And then you can introduce maximum moduli, say Mn supremum.
To have a situation as in theorem B and to the scale.
No. In B there is a sequence of maps.
Yeah, but
Here there's
notation is not.
You can take in this theorem B just one Fn is just the same F. Then F will be infinitely renormalizable.
Yeah.
Yes, that's an important particular case, but kind of easy. You can take here Fn is equal to F for each n, then you get the infinitely renormalizable. And of course, this condition is automatically okay, because you cannot have small Julia set in the basin of attraction parabolic cycle. That's particular. But in general here, I think it is more interesting than Fn. Okay, so here. And M is supremum of moduli of fundamental annuli, all fundamental annuli. Okay, for K. This is just an they are all comparable by this star, which are bounded from the bound universally. So now, okay, so now if you know this term is positive, then there is no official terminology here, but complete power. And if this falls along subsequence, then it's complete bounds or subsequence. And we call if this sequence tends to 0, then we call it vanishing. When they also on the subsequence. By the way, I did not draw any picture, but from the beginning, having this polynomial-like map should not imagine it like this. It could be like this. For example, this is B and this is some U. Okay. And I recall this because now I plan to talk about history. Which was about complex bounds, finding complex bounds. So Sullivan proved this complex bounds. He introduced this notion and proved complex bounds for infinitely renormalizable quadratic polynomial with real quadratic polynomials and with bounded combinatorics. Right? And he precisely used such polynomial-like maps. Okay. So this interval is very, very tiny if you consider high renormalization, and this is kind of almost infinite in this case. Then Hu and Zhang, they proved local connectivity of the Julia set for the Feigenbaum polynomial. Because Sullivan proved this as a step in understanding Feigenbaum's universality. And that was about Feigenbaum polynomial. I mean, Feigenbaum fixed point, and Feigenbaum, there is also Feigenbaum polynomial. And for this Feigenbaum quadratic polynomial, so this polynomial-like map is with complex bound, but it is not related to the geometry of the Julia set. But there is another without complex bound, but is related, which is built from Yuko's pieces. Okay, and then when you intersect, what they did, they intersected these two polynomial maps and understood that they have the same Julia, small Julias. And then you can, because of complex bound, everything should be small in some sense. But if this is small, then the Julia set is the intersection of all pre-images. So then you get that some pre-image of this puzzle piece is inside of something small. So they're small. And 10 to 0 is together with the real trace. Okay. That's how they prove the global connectivity at 0, and then there is another story with spreading it out. Okay, so local connectivity. Then I think, but they just used this, used this Sullivan's complete bound as I tried to explain. Then there was some result by Lubitsch about essentially bounded combinatorics, I think. But whatever it means, but it's not a general case. But the problem was whether complex bound holds for any infinitely renormalizable quadratic polynomial, and we proved it with Sebastian van Strien. Universal complex bounds. That was in 1994, I remember. Complex bounds for of course, for real unimodal and then we proved universal complex bounds for finitely renormalizable maps, which is, by the way, important in the if I were talking about the example. And then a bit later, Jacek Gracek and Greg Schwenter and also Lubitsch and Polsky proved it by different methods, the inducing. And they use this bound as one of the ingredients in proving density of hyperbolicity of quadratic family in real quadratic family. Okay. Then there was a non-trivial generalization for real maps with several critical points. Simple. I think Shen proved this bounds for unimodal maps, polynomials, and then together with Kozlovsky Shen, they used it. I think Shen produced it. Not sure. I think there was some enhanced nest. I mean, which is something which is not first return map. I think it was very unusual and non-trivial. Which kind of paved the way for all this. Anyway, so they proved density of hyperbolicity in dimension 1, okay, for multimodal maps. And this bound played an important role. But that's about real maps. About complex maps, also there are classes of maps, quadratic polynomials with complex bounds. I think Khan proved complex bounds for an infinitely renormalizable quadratic primitive infinitely renormalizable or bounded combinatorics.
Or complex C, right?
Complex C, of course, yes, which was something. This is, I always amazed by this result. I think that's an outstanding result, proven it for multimodal maps. Okay, so this primitive precisely means that he assumes that there is an infinite sequence of primitive renormalizations with bounded combinatorics. So in between there could be several satellites, but again with everything bounded, because after all the combinatorics here is bounded. Okay, and then complex bound. Then there were series of works with Lubitsch when they proved it for some classes of, for more classes of combinatorics. I'm not sure classes precisely, but what I'm going to talk about, maybe it give a hint what cannot be, combinatorics cannot be in the topics. Okay, why it is very important? I mean, Sullivan used it, and then it implies local connectivity. But for local connectivity, it is enough to have some subsequence of renormalizations in bounds, not all of them. I think that Jeremy Kahn first explicitly proved. Okay, but to conclude local connectivity of the Mandelbrot set at the corresponding F or C. Complex bound, I think, should be like combinatorial. So it should depend, should be universal for any given combinatorics. Okay. So it's okay. So this is what was history probably. No. I mean, there's history of complex bounds, but there were history of no complex bounds, which is essentially about Douady-Hubbard's examples. This is also in the beginning of 90s, I think, of infinitely renormalizable quadratic polynomials with this set, infinitely renormalizable set S, not totally disconnected, containing non-trivial continuum. The component containing critical point already non-trivial here, not totally disconnected, which by Kahn's proof implies that that there is then there is a spatial of vanishing moduli here. Because otherwise, if there was sequence of renormalization with model away from zero, then the whole Julius cycle. Okay, but this is a very particular construction, very nice construction, inductive construction. It was from the beginning, which is by perturbations. For example, it holds only when, first of all renormalizations, all renormalizations are satellite. And with relative periods of periods, Sn relative period very fast go into infinity. But more, you need more here. To each satellite renormalization, one associates a rotation number, okay, in which some iterator f permutes small Julius sets. And so Sn is the denominator of this rotation number, but there is also numerator. So this is rotation number. And in the Douady-Hubbard examples, by the nature of construction, this rotation numbers tend to zero. Usually just one over Sn. So you cannot construct like this with polynomials tending to not to cast. It means that if you consider each time quadratic polynomial corresponding to renormalization, then it means that this quadratic polynomial tending to cast. And you cannot do it tending to some other point. Because it's by small perturbation, so you need this connection. And okay, now let me state so corollary from so assume that f is infinitely normalizable, polynomial, not quadratic necessarily. And assume that there is a sequence of satellite renormalizations along the way, such that k n I plus 1 is subtle. Okay. So if relative period Si. Okay. And the base period is, of course, something very huge. This is the setup. There is a subsequence of satellite relation with the relative period. Okay, yes, Si. Let's just assume that it tends to infinity. Then if there are bounds on the level ni if m ni is positive, so there are bounds on level ni, then on the next level, all this moduli, in fact, not only fundamental annuli, but also root annuli. 10 to 0. Okay. So you cannot have I can explain why holds. Because if we assume bounds here, then we can, first of all, one can arrange that kind of the range of the next normalization is inside of ni plus 1 or inside of a range of ni. Not along the whole sequence, just for such pairs. Okay. And then because of this condition, one can find a polynomial which is hybrid equivalent to this relation by a quasi-conformal conjugacy with bounded distortion. Sequence of quasi-conformal conjugacies, but with bounded distortion because of this. Okay. And but we know from theorem A that for satellite renormalizations of polynomials with relative period going to infinity, root and modular from value, then just come back and get this. So it is an easy corollary. Second, if this infinitely renormalizable set is contains maybe not for this. If, like in Douady-Hubbard example, if components or critical components of S are non-degenerates or not points, like in Douady-Hubbard example, then you can just write down this bound for moduli C over Si, where C is some constant. Okay, so because again, by theorem it does not matter what the base period, it matters what the relative period is and the size of critical component. Okay. So this is one corollary, but okay, so we have this limitation, but still it is kind of conditional. We assume that here it is. But one can write down an explicit condition just for periods which guarantee the vanishing moduli. Let me explore the theorem. Assuming this setup, assume that Ni is the period of Ni. This is the sequence of satellite renormalizations. So if lim in of log Si over Pni positive, then this moduli and this. So you can arrange moduli 10 to 0 along any given sequence of satellite renormalization, but you need very fast growth of relative difference. And if here f is just polynomial. If f is quadratic, then MLC holds at such C. This is by a strange coincidence, because I proved this under this condition in one of my previous. And here we got same condition. For example, if you have, but what is important here, that there are no restrictions whatsoever on the rotation numbers. So such polynomials can tend to any polynomial, for example, if it is quadratic, to any point on the main coordinate. Okay, not only to the cusp. So it's very different from Douady-Hubbard. But of course, the conclusion is weaker, because there the Julia set is not locally connected. Here we only have no model. Okay, and it's a question whether I think the Julia set is not locally connected. I don't know.
Here you have kind of non-local connectors. In the same situation, you prove MLC.
Yes, yes. So you cannot prove MLC here by complex bounds because they don't exist.
Yeah.
This is I proved it by some extension of multipliers result. I think I have no time for example.
Next time.
Well, it's an archive.
It is already on that.
Yes, I mean this is not, but example is an archive.
But the talk is not your theorems A, B.
Yes, they are.
They are.
Yes, they are. This is not. And soon there will be some modifications for rational case. Compared to this archive. Okay.
Do you have questions?
Yes, I have a question. So could you summarize what kind of examples you have when your theorem B applies when the hypotheses are satisfied?
If you apply theorem B to the stationary sequence of OFN F, you immediately get that so what it says? It says that you have infinite renormalizable map. And this condition that K star n tend to some non-trivial, it just means that infinite renormalizable set is not totally disconnected. there are non-trivial components there. And then you get that in this situation there is vanishing moduli. But it was known because it was known, but if there is complex bounds along some sequence, then that's, but that's different.
People online. Christoph,
Yes. I'm present.
I don't know.
Hello.
Who is online? Can you check?
Nobody sleeps.
Thank you.
It's, I don't remember when I gave so long talk.
I think we will make quality so good. You can there's some fear on this seminar,